Right, little resume about myself. I've been in all my working life in the foundry industry. Had many job roles. Started as a trainee methods engineer. Had to do pattern making and technician apprenticeship. Went out as a foundry consultant. Had the ability to teach methods engineering not only in England but parts of the world. Being a foundry manager at a few companies. Technical manager and a vice president of production. Worked in many materials, cast irons, your SGs, your grey irons, very various amount, different types of steels, aerospace alloys and non-ferrous alloys. Having worked in an aluminium foundry in the past and joining Skaigh Engineering as a foundry manager, I always wanted to have a simulation tool. Because in the past I've used Magmasoft, Procast, SolidCast, and all the good pieces of software. However, we chose for our use in the gravity die casting to use InspireCast. Just a little bit about Skaigh Engineering. We was established back in 1965 by George Ripley. Since July 2020, I came on board as a director with Tessa Shaw, Matt Edmondson and Nick Newman, and we're trying to push our foundry into the forefront and be a competitive foundry like the rest of you guys. We employ 28 people and we are putting investment in our foundry. And one of them, like I say, one of the main investments is to have casting simulation. Like I say, I've had 44 years of foundry education experience, and we have a good apprenticeship program, and I need to pass that on to one of our employees in a few months' time. And casting simulation is a good tool. We manufacture aluminium gravity die castings for a wide range of companies across the UK. Several grades of aluminium and zinc. Our casting batch size is 5 to 1,000 components, weighing from 100 grams to 30 kilograms. We're quality assured. We have on-site facilities. We have a tool room. We manufacture shell cores. We do our own heat treatment. We do offer surface finishing that is done off-site. We also have our own machine shop, and obviously we offer casting simulation as a problem solver and also on customer new designs. So what I want to talk to you guys today is on 3 case studies. One on an actuator die casting, one on a new product we've took on board, which is a bleach and beaker halo, and a problem solving on a die casting housing. Right, before I get there, right, what we were like a few years ago is we were good at inheriting people's dies. You know, they've gone around the country, they've gone from foundry to foundry, and we get that die and we have to cast it. So we cast a sample off, and it's always the same. Your sample's always good the first time. Then you go into manufacture and you have a high scrap rate. So obviously you've priced that up to a customer. It's very difficult to go back to a customer and say, right, the scrap rate's this, what do we do? And again, you don't know what that die is going to do, but if we've got it and it's gone around a lot of foundries, we're getting poor quality. Hence increased costs. We find that we get excessive fettling. The gates are not in the right situation, so it's taking time to remove the gates to get back to that near net shape. High scrap rate, might be full of shrinkage, gas porosity, all incurring costs that we can't pass on. And again, long lead times, because if we can't make it, we've now got to spend a lot of time looking at the die, doing sample trials out in the foundry to get where we should have been right at day one. And we always want to do research and development, but doing trials in gravity die is not cheap. You're having to send the die into the tool room, do a trial, cut metal out, not helping the die properties because now you've weakened the die. So it's so hard to do development in a gravity die casting, and we're relying on people's experience on the shop floor, myself and other colleagues. So bringing simulation on board, right, it does reduce the sample time. It's quicker to design. You can work with the customer. You can go from concept, simulate, put your techniques on, look at problems that lie on the part. You might have isolated junctions or sections. Increase quality. You know, if you put it through the simulation tool and it's not showing any indications, you know that the method's correct. What happens on the shop floor is down to your quality control and your assurance, but at least you know you've got the technique right, and so you can problem solve elsewhere. Again, less wastage. It enables you to think out of the box. You can try different manufacturing techniques, different gating techniques. For us, we look at also die section thickness, because that also influences how our casting solidifies. So we can experiment that before we go to the final design. Also, education and awareness, right? This is good because we do share these results to the shop floor. So if we're looking at an existing product, we'll invite a guy from the shop floor who makes that or pours that die, and he might point out something we haven't put as in the data set, and then we can re-simulate it. So we're trying to get to what we're actually doing, pure, proper physics. And again, knowledge, able to interrogate fluid flow and solidification and get accurate problems we can solve out. Right, I want to talk first of, we've got a worn out die, we have a good customer relation, and we need to manufacture a better die. Now, I don't know if it happens in a lot of gravity die casting foundries, but a lot of foundries allow the tool maker to put the manufacturing technique on. Saying that, this particular product is an air actuator, and I've got a schematic model down on the page showing you that we've got core plugs, a 4-part die, and you've got the product and the method of manufacture. This die lasted for 15 years. It made 19,000 saleable parts. However, we must have put actually 24,000 pours into that die, or maybe even more, because we started incurring a lot of scrap rate. With that die, and I'll show you the simulation shortly, is we relied a lot on the shop floor, tilting the die in different orientations to get a correct pour. And we decided with our customer, the die had worn excessively. In the right top corner, you can see the die. I wanted to magnify that, but I do apologize. My software's not allowing me to do that. It would show you a lot of metal erosion over time. Hence, you know, you get large die lines, flash lines that have to be removed. So what we wanted to do is improve the die design. So we started up from the basics, and that was, let's simulate what we currently do. So this is where we're tilting this around about 20 degrees. You can see that we've got 2 metal streams. Not the best technique, but I've got to show you warts and all. From that, obviously, we can improve that. So we've got a proper pouring base and a good target area for the pouring guy to pour into the well. So actually the gating system is controlling the fluid flow. We're not relying on the pourer. Obviously we've got to rely on the pourer because he's got to pour at a steady state into that pouring basin and make sure he gets the right level of metal. But as you see, the metal goes down. We've got it very controlled. Nice wide ingate there to get a nice laminar flow. So yeah, we can see we've got a good flow happening, all levitating or gravitating back into the feeder. So yeah, we've got a good technique. Where do we go from there? Well, in InspireCast, there's a great tool, especially for a die casting foundry, because you're only looking at the fluid flow. What you actually need to do is, in a gravity die, it's not like a sand mold where you've got permeability. You've got solid metal sections and you've got to evacuate the air. So what we can do in InspireCast is we can look at the air being removed out the die. So from the predicted outcome, you can see on the left hand side we have bosses on this actuator part, and that's where we're going to get air entrapment. That can be in the form of a gas bubble in the metal, or if it's trying to get out through the cast section and get entrapped in the solidification, or we can get a rounded cold sort of surface on the edge of the casting. On the right hand side also you can see that we've got, even though we've got a little gradient in the casting, we've got air entrapment on top of the barrel. So the solution, right, is now we go to talk to the tool maker and we can put a vent into the die. Obviously, I've shown you where we've positioned it. We can't put it ideally to the top of where that radius is because that weakens the die, but we can sufficiently put it where we need it, where it doesn't affect the die performance or cause a problem with the die, and we've now removed that. On the one on the right hand side I showed previously, we would put the vent in on the core plugs. Also, what we can do is we can do a validation about the soundness, and we can do a virtual X-ray, and we look at macro shrinkage. So on the left hand side, on the prediction, in the little red regions, that is predicting macro shrinkage. I'm not worried about that because you can see in the top wireframe model, we have macro shrinkage in the feeder, and in the lower part on the running system. We always validate, like most foundries, we cut castings up, and on the right hand side that shows you the section illustrating that that casting had no macro shrinkage. With aluminium, not only macro, but I could say that with a lot of cast materials, we need to look at micro shrinkage. I have to go on my soapbox here. Please do not use porosity, because porosity means a multiple of sins. When you're predicting the right defect, you have to give it the right defect name. Porosity means porous, but what is porous? Is it gas? Is it macro? Is it micro shrinkage? Is it oxides? All encompasses. So let's not talk about porosity. Let's actually call what the defect is. So we're now looking at micro shrinkage. We can see there's a small amount in the center section around the boss area. This is a prediction, and also in the gate, which we don't care if we have porosity in the gate because that gets removed. On the right hand side, again, we validated it. I have to apologize for this slide because we don't have the best facilities to do a dye penetrant. And when we did this dye penetrant, we had dust in the area. So those nice purple blobs or specks are actually dust that the dye, when we try to wipe the dye off with the developer, we caught. But there's no, I can assure you, there's no porosity in there. That's just particles that absorb the dust. And hence that was a free porosity casting. I'm saying porosity, but micro shrinkage. The second one I want to talk about in the case study is the Belisha Beacon Halo. One of our new customers came on board and wanted us to design the halo that goes round a Belisha beacon. Right, now this is a thin wall casting, and we had to think seriously. Obviously, we have to be competitive and we have to look at the design. Now, a lot of large thin wall castings in the past at Skaigh, we use a two-man pour to get the metal into the die. One of the criteria to get the price down was actually to do a single pour. So we just have one pourer to pour the metal. And we set ourselves some targets. So obviously, as I mentioned, to have a single pour, obviously we want to provide a casting that's defect free. We want to manufacture the casting as the highest quality we can produce. But on top of that, with my production head on, I want to produce as many as I can a day without affecting quality. Again, helping the customer get the part to the market quickly, which we did. And I don't want to be doing lots of trials. I want to make the die right first time. And that's the target. We want it right first time, hence using casting simulation. And out of all this, we want to reduce the product development cost. So we did a filling analysis. As you can see, it's a single pour down, a single control down sprue. We need to get the metal distributed evenly throughout the casting, so we have multiple gates around that casting. So yeah, it looks all nice and pretty. Nice laminar fill, but we can go a little bit better than that. So one of the rules that we have in the foundry industry, we shouldn't exceed 0.5 meter a second. What you can look at is the velocity in the simulation. And what I want to illustrate here is that we didn't, as the metal got into the casting cavity, we didn't exceed that rule. So you can see a lovely laminar fill, all the gates and the metal meeting along the spoke. It's all nice and dandy showing this simulation, but I'm interested in a good casting. So we looked at the predicted macro shrinkage for this part. We had a shrinkage-free defect casting. This part is machined all over. On the right-hand side, we can illustrate we had a nice quality casting that we could ship to the customer. Right, the final case study I'd like to present is when you have a problem in the foundry, right? And you've got to sort of strategize what we're going to do. Even though I'm an experienced engineer and foundryman, we all can be took back where we try things and they don't work. Hence, I like casting simulation, right? So we don't have the problem, so we can look at the method and the technique we've done. Now, like I said at the beginning, you can do the casting simulation, and if it's tuned in correctly, you know the technique's right. Because like I say, the operators can influence a good and a bad casting if you haven't done everything correct and put the right data in. And you've got to have the right pouring temperature, the right die temperature, and make sure for us as a gravity die casting, we use the right die coatings, have the right viscosity of the die coatings, they're applied in the correct technique, right? So the strategy is analyze the filling solidification, pick the outcomes of the current technique. So we need to go out to the foundry and get the right data, and then determine how and why this occurs. So like I say, we'll do the simulation. We can resolve problems by redesigning the part. If we can go back to the customer, some customers are still where it's a tried and tested design and they won't change, but we do have a lot of customers who will willing to change, and we have to change the manufacturing method. And if we've found that our technique's wrong, we can redesign the technique and modify the tooling where necessary once we've done the simulation. Right, so what's the defect? Well, what we've got is we've got holes that appear surface and subsurface. So what I'm showing in that photograph there is the surface defects. I apologize, we seem to have lost the section of the one where we took it through the section, but it's of a similar ilk defect. So what we did is we did a filling analysis. This is a twin pour. This is a 35 kilogram poured weight. So as you see, the metal goes through into the pouring basins. To me, that looks a very good fill. Nice laminar fill, no turbulence, got the gates in the right order. So should be good. Let's look at the defect predictions. So we look at the macro. The casting doesn't contain any macro shrinkage. We are aware in some of the fin wall sections, we have some micro shrinkage. That doesn't cause a problem to the customer. And it looks excessively there, but on the cast sections, it's very minor. Really have to look under a microscope to find it. However, as I mentioned before, I want to look at the last air. Absolutely brilliant tool. I'll let this run a few times for people to analyze. So you're looking where last air remains in the die, which can get trapped as the casting solidifies. I'll give it one more time. Right, what we found on the predicted results is we were getting air trapped in that area, in that location. Like I say, I didn't have all the photos I could show you, but we were predicting trapped air on the left-hand side and on the right side, similar to the photograph I showed you originally. Right, we had to redesign the part to overcome that, go back and cut into the die. Put larger fillets in the junction to allow that gas to escape. Even though there was a gradient on the casting, you would have believed that, you know, we wouldn't have entrapped air. Obviously, I have a limited time, so obviously I condensed a lot of what I was presenting, but there's lots of fields in InspireCast, like many simulation software packages, where you can look at velocity vectors, you can look at other result files, and get similar results. Right, finally, to sum everything up, right, we give this software our approval. We've been very, very happy with it. Well delighted with this software. We love how the mesh is generated. I don't want to talk about other people's mesh. I'm not here to discredit or announce other people's software, but we really love the mesh generation. Remember, you've got to put good information in. Good information will come out in your results of your simulation. So it's helped us resolve casting issues that can't be resolved by our experience. Produces an interface between product design and casting process. What it does do, it increases customer confidence. We share these results with our customers. You know, we don't charge for them if we've made the die. If we've inherited the die, there will be a little charge. It aids a better understanding of the casting solidification and fluid flow. I'm nearly 61 and I'm always learning. And I think everybody's always learning. And this is a good tool to learn from. Helps in trying out theories without costly manufacturers have illustrated. There's lots of things you can do. You know, it's, you know, you learn the theory, you've got to put it in practice. And cost savings and reduced scrap and yield improvement. We're seeing that a lot. And we're always, with our customers, asked to keep the casting price down. Well, obviously we compete not with friends in England, but European foundries and China. And we try to keep the cost down to where we can actually make a profit, because that's what we're here for. Okay, that sums my presentation up, guys. Thank you very much.